All right, so determinant of a matrix, it's got to be a square matrix. Same number of rows as columns. So 3 by 3, 2 by 2, that sort of thing. Different notation for determinant. One of those notations is just abbreviating the word determinant with DET and parentheses, and then you'd have the matrix in there. And I'll just, we'll write a 2 by 2. That's short and quick. That's one way that they might denote for you to tell you to find the determinant, is to write it like that. Or they will use this notation, which looks like absolute value bars. So it's a matrix. When you just write a matrix, has brackets on the outside. If it doesn't have the little tails on it to make it a bracket, it's a straight up and down bar. What that means is determinant of that matrix. So anytime you see a matrix in what looks like absolute value marks, that means find the determinant, is what that means out of that. So a 2 by 2, you guys know kind of the order we did operations. A lot of things, some of them are easy to do by hand. So easy to do by hand that I would not do them with the calculator. Others, not quite as easy to do by hand, so the calculator makes it handy. So 2 by 2s are small and they're easy to do by hand. Ashton, can you please take the earbud out of your ear? Thank you. All right, so 2 by 2s, really easy to do by hand. All you've got to do to find the determinant of a 2 by 2, so let's just use the letters and then we'll do an example with numbers, is multiply the diagonals. A times D, and then subtract B times C. And that gets you a single number that is the determinant of that matrix. For a 2 by 2, it is that easy. An example, if I gave you 5, 4, -3, 7, just a 2 by 2 matrix, I'm using the notation that looks like absolute value bars, because it's harder to recognize. If you see that, you know what it's saying to do. So I'm using that notation just that gets us looking for it. And really easy to do. 5 times 7 minus 4 times -3. And I'm writing that extra step out. I would expect you to just do that multiplication in your head and get 28 minus -12, which would be not 28, 35. 35 minus -12, which would be 47, would be the value of the determinant. The determinant is a number, and as long as that number is not 0, that means that is an invertible matrix, is what that means. So if the determinant ends up being 0, we're going to talk about in a little bit a thing called invertible matrix. So anytime you find a determinant, really you're usually doing that in order to decide if that matrix, if it has an inverse. It will have an inverse as long as the determinant is not 0. So that's what that determinant can help us determine. That's where the name comes from. So 2 by 2, I would normally do by hand instead of taking all the time that we're going to show here and going to the calculator and hitting second matrix, going over to edit, and then a 2 by 2, and then typing in 5, 4, -3, 7, getting out of that. And then to find the determinant of a matrix with the calculator, you hit second matrix, and then you're doing some math with it. So we're going to go to the math menu, and the very first option is DET. That's the determinant. You hit DET, and then you tell it what to find the determinant of. I put that in matrix A, and we get the same number. All of that typing in when we could have just multiplied and subtracted and got it. So 2 by 2s, I normally just do in my head or by hand, just because they're so short. 3 by 3s are not quite as short, so that's where the calculator can come in handy for that. So let's look at a 3 by 3. And I'll show you one method for finding the determinant. I'll show you how to do it by hand, and then we'll do it with the calculator as well. you take, if you're going to go into engineering or something, you're probably going to have a class that's related to linear algebra, and you'll probably have to do some of these by hand. I want to show you that it can be done by hand, but it's not very much fun, okay? One of the methods for doing a 3x3 by hand is to take the first two columns and copy them again. So I would copy over 6, -1, 3, 5, 8, -4. Just the first two columns. Then you take the diagonals, and the ones that go this direction that have 3 numbers in them, you're going to multiply all 3 numbers together in that diagonal. So we would say 6 times 8 times 0. We would add that together with 5 times 11 times 3. And then we would add that together with 0 times 1 times -4. And then we would subtract the sum of the other direction diagonals. Their products. So I'll go the other direction. 0 times 8 times 3. Six times 11 times -4. 5 times -1 times 0. I would work these out. So here, this is easy because you got to multiply by 0, so that's going to, that whole thing's going to be 0. That whole thing's going to be 0. So we end up with 5 times 11 times 3, which would be 55 times 3 would be 165. I think. Check and see. Yeah, that's good. And then on the bottom part here, the other direction, the positive slope diagonals, I guess the best way to describe those, we'd have 0 plus 66 times -4 would be -240, -284, and then that's 0 again. So we have minus -284. I think that's right. Let's check and see. 6 times 11 times -4. -264. Excuse me. And then when we subtract that, so 165 minus -264. Positive 429. So that tells us that that's an invertible matrix, is what that tells us. Tells us the determinant is 429. There are other things that we can do with the determinant, but one of the things that we're going to use it with in Algebra 2 is deciding if a matrix is invertible or not. If it's not invertible, the determinant will be 0. If it is invertible, it'll be anything else. Okay? 0 is the only thing as a determinant that makes it go on. Now, that's one method for doing 3x3s. 4x4s, that method doesn't work anymore. 5x5s, that method doesn't work anymore. That only works for 3x3s. So anything bigger than a 2x2, I tend to suggest doing them with the calculator. Just because, look at how many operations that was. That's 3, 6, 9, well, we can call that as 1, 2, 3, 4, 5, 6, and then 7, 8, 9, 10, and 11 operation for a 3x3. A 4x4 is a lot more than that, depending on what numbers are in it. So 3x3s I would do with the calculator. So I would go to the calculator and hit matrix, go to edit, and I'm just going to put it in matrix A, 3x3, and just put the original in there, which was 6, 5, 0, -1, 8, 11, 3, negative 4, 0. So that was the original matrix. 6, 5, 0, negative 1, 8, 11, 3, negative 4, 0 was the original matrix. Second quit, second matrix, go to math, determinant, matrix A. And we get 429, which is the same thing we got by doing it by hand. That was probably easier to type in and do than it was to actually do it. So anything bigger than a 2x2, I suggest you use the calculator to do that. There are methods for doing them by hand, several different ways of doing that. Is it something you're going to need at the grocery store? Probably not. But is it something you'll need maybe if you're going into engineering, electronics, or something like that? Yeah, you probably will have a course that will ask you to do a little bit more. So I want to show you that you can do it by hand, but it's not real pretty and it's not nice. The calculator is going to be your friend on doing those. Anything bigger than a 2x2, do with the calculator. That's what I'm saying. All right. The next thing that we're going to do, that's again a matrix specific thing, is row operations. And row operations are a pretty simple idea. So what's going to happen here is you're going to get a matrix. Let's put that as a 1 so we don't have any repeated numbers. So we got 2, negative 4, 8 in the first row and 10, 6, 1 in the second row. That's a 2x3 matrix. Row operations do not matter what size they are to start with. Okay? Doesn't matter what size because you're not combining it with a different matrix. You're just taking this matrix and doing a row operation or multiple row operations for that. So with row operations, what it is you're taking a set of instructions. They're going to tell you what they want you to do. So for this one, let's do this row operation. Let's say we had negative 5 times row 1 plus row 2, and we want to change row 1. Okay? This tells you which row is changing. Okay? Change that one. Don't change row 2 on your answer. Row 2 stays the same. Row 1 is the one that's changing because that's what it said to change. Okay, whatever it tells you at the end is the result. That's the row that's changing. So when you go to do this work, your answer, you're going to write a matrix, and I'm going to copy row 2 before I do anything because I know row 2 is not changing. So 10, 6, 1. Row 2 should be 10, 6, 1 because this row operation said change row 1, not change row 2. We're going to use row 2 to change it, but we're only changing row 1. So then you just do the instructions. The instructions say negative 5 times row 1, and then add that answer to row 2 and write that new answer in row 1. So we're going to take negative 5 times 2, which is negative 10, and we're going to add that to row 2. Negative 10 plus positive 10 is 0. So we're going to put a 0 right there in that spot. And then we're going to do the next piece. Negative 5 times negative 4 would be positive 20 plus row 2, so plus 6, 26. And then we take negative 5 times 8, negative 40, plus 1, negative 39. That matrix right there is your answer. That's what a row operation does. It tells you what to do and tells you what to change. Don't overthink those. It is straightforward like that. We're going to do another one. Let's take this matrix. 2, negative 3, 6, 10, 1, 5, 11, negative 2. And then the last row is 4, 7, 10, negative 10. So that's a 3 by 4 matrix. And the row operation that we want to do is negative row 1 plus row 3, changing row 3. Negative row 1 plus row 3, change row 3. So when I go to write my answer, which rows are not changing? 1 and 2. 2, negative 3, 6, 10, 1, 5, 11, negative 2. Those rows staying the same. Row 3 is the only one that is going to change. And it's going to change by this set of instructions. Opposite of row 1 plus row 3. So the opposite of 2, negative 2 plus 4, positive 2. Opposite of negative 3, positive 3 plus 7, 10. Opposite of 6 plus 10, 4. Opposite of 10 plus negative 10, negative 20. Row operations, you don't need to put them in the calculator to do. It's much more complicated to get the calculator to do. It'll do row operations, but it's not easy to make it do them correctly. So I don't even show you how to do it with the calculator because it's so easy to do without one. Okay, and it's so easy to make a mistake with getting the calculator to do it. Okay, very, very easy thing. Row operations, straightforward. All right. Now, go to the inverse of a matrix. Okay, inverse matrices or invertible matrices. Let's change that. Invertible. That's a better way to say it. It's a better word. Invertible matrices have a non-zero determinant. That means the determinant is something other than 0. It can be a positive number, it can be a negative number, and it's okay. If it's anything other than 0, you can find the inverse. Okay, so if you're given a matrix and they want to say that the question is does this matrix have an inverse? It's not necessarily saying find the inverse, it's saying does it have one? Check the determinant. If it's 0, then the answer is no. If the answer is anything other than 0, then it does have an inverse matrix. Okay, so inverse matrices are something that is very easily done with the calculator, not nearly easily done without the calculator. Let's look at a matrix. So I don't know what letter we're on here. E. Find the inverse matrix. So let's say matrix A, we'll call it matrix A, is this 2 by 2, 4, negative 7, 6, 10. And we want to find the inverse of that. Well, let's make sure that there is an inverse. Since it's a 2 by 2, the determinant's easy. 4 times 10 is 40 minus 42, negative 42. So that's something other than 0. Doesn't necessarily matter that it's 82, but we know it's not 0. Okay, so we know we can find the inverse. Now, the way you would do this by hand is you would set up a identity matrix over here, which we'll talk about in just a minute. And then you would have to come up with the row operations in order to convert this matrix into the identity matrix, and then what's over here would be your inverse. That's a lot of row operations, depending on the matrix and the numbers that are in there, and the path that you take, how many it takes. There's not always a set way. I don't prefer you to do it that way. If you want to know how to do it that way, you can come see me and I will show you. But I just say, let's just use the calculator to find that inverse on this. So the inverse matrix, the way you're going to do that, to find the inverse, the notation for that is A with the name of the matrix with a little -1 exponent. That means A inverse. That's the inverse matrix. So put that matrix in your calculator. Second matrix. I go to edit. I'm just going to use A since that's what we call this one. Matrix A. And then I'm putting in 4, -7, 6, and 10. Okay. Oh. Thank you. Technology is wonderful. Works. We're back. All right, so we're got that calculator. We put in that matrix at 2 by 2, 4, -7, 6, 10 into that. So second mode to get back to the regular calculator screen. And then you want to just go and grab the name of that matrix that you put in. So I'm going to hit second matrix, and I put that in matrix A. So I want to pull it up like I was going to do an addition problem or a multiplication problem. So I pull it into there. And then your calculator has an inverse button. It is right here. It's the x to the -1 power. That's the inverse button. So you're going to hit that, and it's going to give you